This is General Dave, a commander for the United States Continental Army during the Revolutionary War. This is a British fort. It's about a 13 days march from General Dave and his forces, and he's planning to attack it. Obviously, with the war going on, he wants to do this as quickly as possible, but there are some things he needs to do first. General Dave needs to march his army to a camp that's about halfway between him and the fort. He needs to send messengers to General Bragg, who's going to join forces with him for the attack. He needs to raid a British armory to supply his troops. He needs to inoculate his forces against the ongoing smallpox epidemic. And as you can see, this is going to get a bit complicated, so let's lay things out more simply. I'll summarize General Dave's tasks as well as how long they take in this table, and for simplicity, let's label them A through K. So, looking at this, can we figure out the shortest possible time it could take General Dave to launch the attack? If we add up the times it takes to do each task, that would clearly be too long, as some tasks, like two different armies marching, can be done at the same time. But it's not as simple as doing all the tasks at the same time. The last column on the right now shows each task that needs to be completed before its corresponding one can be started. So we can start A and B immediately, but everything else has at least one prerequisite. Complicated, right? Luckily, there's a simple method of determining the shortest possible time it would take to complete all of these tasks. We need to start by building a network. This is our starting point. I'll represent each task with a node that is connected with an arrow to any task for which it is a prerequisite. We can start A and B right away, and going from there we can build this network. K is the last thing that needs to be completed, so from there we can progress to the end, attacking the British fort. I'll also label each path with how long it takes to complete the previous task. For instance, it takes 6 days after starting A before starting C and D, and so on. Now recall our table of tasks. Hopefully you can see how the network was constructed. Now let's use the task's lengths to determine how early we can attack the fort. Let's label the top half of each node with the earliest possible time we can start that task. This is a method we call forward scanning. A and B are obviously day 0, since they can be started right away. Then, since it takes 6 days to do A, the earliest time we can start C is 0 plus 6, which is day 6, and so on. Now up to this point, the forward scanning has been simple, but take a look at task H. Calculating the earliest start time from E gives us a different result than from G. However, note that the converging connection means that we need to complete both E and G before starting H, so we can only start it after the last of the two tasks is completed. This means we must take the largest result of forward scanning between E and G, which is the 11 plus 4 days from G. Thus, the earliest we can start H is day 15. Using the same conclusion, note that H is a limiting factor for J, so although F can be completed by day 14, we can't start J until day 17. Let's continue forward scanning to the end now. There we have it! The shortest possible time it can take for General Dave to attack the British fort is 21 days. But this doesn't tell him everything. We can glean some more information from this network, so let's do some backward scanning. I'll label the bottom half of each node with the latest possible time that task can be started while still staying on pace for the 21-day finish. To backward scan to a previous node, we just need to subtract the time it takes to complete that task from our current node's latest start time. Now, what happens when we reach a spot with two different results, like G? While forward scanning, we took the largest of the two numbers, but if we take 17 minus 4, which is 13, rather than 15 minus 4, which is 11, we couldn't start H until day 17, and that would delay the entire progression and therefore the attack. Thus, when two paths converge during backward scanning, we need to take the smallest of the two results, which in this case is day 11. Now let's finish up our backward scanning. And with that conclusion, A must be started immediately rather than by day 3. So take a look at this completed network. Note that we have a path of tasks from start to finish that must be started as soon as possible to stay on pace to attack in that shortest possible 21 days. We call this the critical path. So What does this tell General Dave? These are the tasks along the critical path, and these are the ones that are not. From this information, General Dave knows not only that it will take him at least 21 days to attack the fort, but that to keep that pace, he must start the red-labeled tasks as soon as they can be, while he has some leeway on the others. This is important information to have, as he now knows how to direct his efforts when needed, and that if it's possible to shorten any completion times, he should focus on the tasks on the critical path. Armed with this information, General Dave is ready to plan and launch his assault. Watch out, Loyalist scum.